Welcome back. We're going to start with example 7.4.5, where we're told that the joint density function for x and y is given here, and we're asked to show that x and y are independent, which means that our goal is going to be to show that, f of xy, the density function, is equal to f sub x of x times f sub y of y, the product of the marginals. So to do that, we better start by finding these two marginals. And so f sub x of x is the integral from minus infinity to infinity of f of xy dy. We're integrating out the y, so we should know what the support looks like. And we are given the support right here. So x goes from 0 to 2, y goes from 0 to 3. So we have a lovely rectangular support. So because of Fubini's theorem, we don't need to mess around with bounds that have variables in them. And so we are going to integrate from 0 to 3 of 1/9 xy dy. So I have 1/18th xy squared from 0 to 3, which gives me 9/18 x minus 0, or just 1/2 x. So there is the marginal density function of x. And now we're going to do the same thing for y. F sub y of y is the integral from minus infinity to infinity of f of xy dx this time. So we're integrating out the x to leave a function of y. X goes from 0 to 2, and so we're integrating the same density function, this time with respect to x, and so the antiderivative that we want is going to be 1/18th x squared y from 0 to 2 this time, and so that gives us 4/18 y minus 0, or 2/9 y. And so the product, f sub x of x times f sub y of y, is equal to 1/2 x times 2/9 y, which is nice. Those 2's cancel out, and I get 1/9 of xy, which is indeed the density, the joint density function, and therefore I can conclude that x and y are independent. Now the next little theorem here says, well, that actually isn't a coincidence, because, well, theorem 7.4.2 says let x and y have joint probability density function f of xy that is positive on a rectangle like we had in the previous example, AB cross CD and 0 elsewhere. Then x and y are independent if and only if f of xy can be factored as two separate functions, g of x times f of y, where both g of x and f of y are non-negative. Now there's a couple things to note here, that this doesn't necessarily mean that g of x is the marginal f sub x of x, or that f sub y is the, I've got this backwards, don't I? Or that h of y is the marginal f sub y of y, right? So up here in the previous example, we could have said, well, look, f of xy can be written as 1/9 x times y. We're on a rectangle. Both of these are non-negative on that rectangle, and so we're thinking that g of x could be 1/9 x, and h of y could be, well, just y. And those are not the marginal functions that we got, right? In fact, there's infinitely many ways. We ended up by crossing off these 2's, but just for example, we could have a 3 or a 9 or a 12 or whatever there, right? Or, I mean, there's so many ways. There's so many ways that these functions could have turned out. to simplify down to this. So just because the function is factorable doesn't mean that you can necessarily guess immediately what the marginals are going to be, right? There's more than one way of factoring things, and the marginals are just one of those ways of factoring. So that's the first note. The second note says if x and y are dependent, if x and y are dependent, it might still be possible for the density function to factor into separate functions of x and y, even if the support is not a rectangle. So just watch out to what the theorem is actually saying. In the next video, we'll do example 7.4.6, which is an application, a bit of a word problem, an application of independence to solve an actual real-world type of scenario.